Like everything, we need to have a place to begin. So we're going to start with units, numbers, and scientific notation. In science, in astronomy, and other sciences, we use a lot of numbers. And numbers are great, except they need to have some kind of a context to make sense, right? If I tell you that you've got a table, and that table has a length of 4, well, that doesn't really help you, right? It's for what? We need to have some kind of a context and some kind of a scale. So units are a way of providing context for numbers. If I've got a number like 4, it helps to know what does that 4 represent. For feet, for inches, centimeters, meters, kilograms. Now we're not even talking about a distance anymore. Seconds. Now we're really talking about something different. The units are going to give a context for a raw number. Now the units that we use in astronomy we generally use a metric system. And the metric system has what's called an SI unit. It's an international standard unit, but the term isn't in English, so it's standard international units. So these have a baseline that we're able to work with. Generally, SI units, we have a unit for length, time, mass. Those are the big ones that we are worried about. We've got a couple other properties like charge, spin, or what have you. But the ones we are worried about are right here. Length, time, and mass. The SI unit for length is the meter, which gets a letter M, lowercase m. The SI unit for time is a second, which gets a lowercase s, or sometimes SEC, just because an S can start to look like a 5. And for mass is the kilogram. kg. So we have a set of units we can mess with. A meter is about 3 feet, a little bit more. Think yardstick, or think almost half of your wingspan, right? This is a good unit of measure, except when we're dealing with astronomy, that's probably going to be a little bit smaller than what we need. So when we deal with numbers in meters in astronomy, we are probably going to be dealing with millions or billions or trillions of meters. And so we end up with a system that needs to be expanded out in scale also. So we add a couple of other units onto the SI system. We have meters for our SI unit, but for the sake of practicality, we will also add light years, LY, and parsecs. Which are PC. For time, seconds makes sense. We're going to end up with some of that, but probably we'll do some in years also. And for mass, kilograms, that actually ends up being what we deal with. So SI units are over here, and these are extensions for convenience. A couple of quick notes about these units. A light year It says year right in there, but this is the distance that light travels in 1 year. Now light moves really fast. It moves 300 million meters per second. So, in 1 second, light moves 300 million miles, or meters. That's a lot. The distance that light travels in a year is going to be, well, a whole lot more than that. So this is a good measure because it gives you something that scales out pretty easily. We also do deviate from this measurement a little bit. So we've got light years, and then we try and be some kind of clever with it, and we'll have like light seconds, light minutes, that kind of thing, which are not really official units, but they're pretty commonly used. The distance from the Earth to the Sun, for example, is about 8 light minutes. What that translates to is if you shine a flashlight from here, the light from that flashlight will take 8 minutes to reach the sun. So, light minutes. Parsecs, they're even bigger. A parsec one parsec is about 3.26 light years. I'm not too worried about whether you know those numbers very specifically, but what I want you to get out of this, a light year is a big distance. A parsec is even bigger. That's the big thing we need. The definition of a parsec comes from some spatial things. So there is a context to it. 3.26 isn't exactly arbitrary, but it's bigger than a light year. That's what we need. So those are the SI units and the extensions. We also use, with the metric system, some prefixes. And you've used some of these before. Maybe not all of them. We use milli, which is a lowercase m, centi, lowercase c. We'll use kilo, which is a K. Mega is a capital M, giga, capital G. We've got some that we use that are smaller than milli. We use like micro and nano. Those don't have a whole ton of astronomy application right now. And when we get to a point where they do, then I'll bring those up. But a milli is like multiplying by 0.001. Centi is like multiplying by 0.01, so it's 1/100th of the unit. A centimeter is 1/100th of a meter. Kilo is times 1,000. Mega is times 1,000,000. Giga is times 1,000,000,000. And these are numbers that up until the last, 25 years or so, we didn't have too much reason to use these very often, but now, especially with computer file drive sizes and such, now these numbers are becoming a whole lot more familiar. Mega, giga, tera. They're numbers that we actually start to use in the real world. So that's it for units. And then numbers, that's kind of in there too. I want to talk about scientific notation. So scientific notation uses the idea of powers of 10 to make things work, to give things a little bit more context without having to write a whole lot of zeros. if I write a number like this, 32, let's put that many zeros, I didn't really count. That gets to be tedious to mess around with. So instead we write this in scientific notation. Now scientific notation takes this number and breaks it into a base number. So we want this to be in a base number. And we're going to go times 10 to the power of some exponent. This base is a one-digit number, one digit before the decimal. So if I'm going to take this number and put a decimal point in somewhere so that this is one digit before the decimal, I'm going to put that decimal point right here. So in this case, my base is going to be 3.2. And then I'm going to multiply by 10 to the power of, and I have to count how many spots I need to move this decimal to get it back to the original number. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. I'm moving this 13 spaces to get it back to the original position. So this is going to be times 10 to the power of 13. If I had a number like this, I'm going to stick a decimal somewhere that makes this into a one digit before the decimal number, and that is right here. Now it's 8 point something, 8.25. And then I'm going to put times 10 to the power of, and I need to see where this thing has to go to get it back to where, to get the point back to where it was. So I'm going to move left 1, 2, 3, 4 spaces. This time I move to the left, so it's going to be a negative exponent. If I had 3.6 or 36000, I'm going to stick my decimal right here, and I'm going to move it 1, 2, 3, 4, 5. So this is going to be 3.6 times 10 to the 5th power. And that gets me into scientific notation. These are going to be helpful because it means that I can express a number like this, which would be, what, 32 million, billion, trillion, 32 trillion, which is unwieldy with all those zeros, and I can write it in a number, or in a way that makes it a whole lot more accessible. That's what I'm doing with scientific notation. I've got a couple of videos for you, and those will kind of walk through this too, but this is the basic idea.